So we start with a mass in a constant gravitational field. This is one that you are familiar with. Ladies and gentlemen, people, what is the direction of this constant electric field?
Down.
Down. What is its magnitude? The magnitude of the constant electric field you are presently in, class. Wow. Let's try that again. Class, what's the magnitude of the gravitational field you are in right now?
9.8.
Well, what magnitude? We already got the direction. The direction evidently was easy. It's the magnitude that's difficult for some reason. We'll try it again with dimensions. Ladies and gentlemen, people, the magnitude of the gravitational field you are presently in.
9.8.
No, that was difficult. Okay, here we go. If I take this mass in this constant gravitational field and I let go of it, you already know what happens. It does that. There is a force of gravity that acts on it that pulls it down. I agree. It's going to accelerate downward. In terms of energy, what happens, Jessica? Sure. In terms of energy, what happens? I have the mass all the way up here. I let go of it. What happens in terms of energy? The energy does not go down with the ball. That's not what I'm looking for. Learner, help us out.
The mechanical energy stays constant, and it's just that the potential energy, gravitational potential energy, is converted to the kinetic energy.
The mechanical energy is conserved because there's no friction. It starts out with gravitational potential energy. If we set the zero line at the floor, when I let go of it, that gravitational potential energy decreases. The kinetic energy increases. Let's instead set up an electric field, which is constant and pointed down. When I take this positive charge in this electric field, there is an electric force. Class, what direction? Please point. The electric force on this positive charge is then going to be. Your hands. Are you having issues with your hands, Curry? Yeah, I'm sorry to hear that. That's difficult. It's going to be down. So when I let go of it, class, what's going to happen to this positive charge? It's going to go down. It's going to accelerate downward. Now this looks familiar. In terms of energy, what happens, Mr. Curry, with this positive charge?
It gains energy.
Does it gain energy? No, it's not going to gain energy. What happens in terms of energy to this positive charge? True, it's conserved. We're drawing a parallel here. We already know what happens in terms of gravity. What happens in terms of this positive charge? Nicola.
I'm going to hazard a guess and say it has electrical potential energy.
And what happens to that electric potential energy?
It's converted to kinetic energy.
We're going to have a decrease in electric potential energy, and it's going to be converted to kinetic energy in the exact same way that we had gravitational potential energy that was converted to kinetic energy. So notice the similarity here. Where we have the force of gravity, we are going to have a gravitational potential energy. Where we have an electric force, we are therefore going to have an electric potential energy. But PE sub E is already taken. Rutherford, what does it stand for? Elastic potential energy. So alas, I put PE sub EL, which doesn't help either because that still could be elastic. So we need to go all the way to the E. ELE, electric potential energy. In order to understand the equation, oh, actually, let's do this first. So we can have conservation of mechanical energy, and there are now 4 types of mechanical energy. Nick, what are all 4 types of mechanical energy, please?
Electric potential energy, gravitational potential energy, kinetic energy, and elastic potential energy.
So notice we now have 4 different types of mechanical energy that we could have when we're talking about conservation of mechanical energy. In order to understand the equation for electric potential energy, we're actually going to start with the equation for gravitational potential energy and kind of review that one first. So the equation for gravitational potential energy, Nick Smith. Gravitational potential energy.
No, it's
mgh, gravitational potential energy. M, mass. G, the acceleration of gravity. We've already talked about that one. H is what, Pooja? The height above the zero line. I'm looking for one word in front of height. It's an important one. It'll get to the distinction with this electric potential energy. What is the word that goes in front of height? Sims. It's an important one that you overlook because you simply assume that it is always true, and so you just do it, but you don't think about it. We have many bus drivers. We just need some of them to actually show their ID and take the wheel. Pooja. Sometimes it can be negative, so it's not positive or negative. Danaher. Vertical. Notice it is the vertical height above the zero line. Vertical. So if we have a constant gravitational field, which looks like this, we can have a mass that is going to be at some sort of height above the zero line, and that vertical height above the zero line we can illustrate like that. The equation for electric potential energy, PE sub ELE. Now notice this equation is actually the change in electric potential energy. We don't have an equation yet for just the electric potential energy, but the change in electric potential energy is equal to negative Q E delta D, where Q is the charge we're talking about. And please notice you must use the positive and the negative, or the negative. E is the electric field, and it needs to be a constant electric field. This is the equation for the change in electric potential energy in a constant electric field. And lastly, delta D, the displacement of the charged particle. This is the displacement parallel to the electric field. So to draw a parallel, we have our constant electric field. We can have a positive charge in that constant electric field. If we let go of it, it's going to accelerate downward, and it would end down here, and we would have our initial final points, and we would have a displacement, and that would be delta D right there. Notice that this is the displacement. In this particular case, it would be vertical, right? It would be the vertical displacement. Now, the reason we can always simply refer to the height above the zero line as a vertical height above the zero line is because the gravitational field is always vertical. But the electric field is not always vertical. So instead of saying the vertical displacement of the charge, we have to say the displacement of the charge parallel to the electric field. So they are very similar. And notice the similarities between these two equations. Instead of mass, we have charge. Instead of gravitational field, we have the electric field. And instead of the vertical height above the zero line, we have the displacement parallel to the electric field. So they are very similar equations. The dimensions on electric potential energy. Dimensions on electric potential energy, please. Christine, dimensions on, let's start with charge. Right, I'm looking for the dimensions. I agree the charge could be positive or negative, but I'm just looking for the dimensions. Coulombs multiplied by the dimensions on the electric field. Newtons per coulomb, and the dimension on the displacement parallel to the electric field. So the coulombs cancel out, and we're going to get newtons times meters. A Newton meter class is a joule. So again, all of these different types of energies, excuse me, are in the same dimensions. They're all in joule. Yeah. Please notice that if this is the displacement, the delta displacement is the delta D is the displacement parallel to the electric field. If it's in the same direction, it would be a positive displacement. If it's in the opposite direction, that displacement would be negative. If you're going opposite the direction of the electric field.